So, hi and welcome to the new lecture. Um, um, Today we're going to talk about file systems. Um, Last time during the lecture, I actually said that we'll continue talking about the memory subsystem, but since it's almost the end of the semester and I would really like you guys to basically get some time to study and stuff, so I decided that I will give the lecture on file systems so that we can post the last the last programming assignment, so that you can start working on it right away. And then we will have one more video lecture, which will be more on the memory. So we are sort of like shifting back and forth. And then I will have a lecture that is more like stuff that I would like you guys to know that is not part of the exam and not part of anything. You can watch it as, yeah, whenever you feel like, if you ever feel like. And this is basically the stuff that I discussed about the REST interfaces and some stuff that is missing actually from some of the courses. And I just thought that why not just give you some idea about what this stuff is all about. So, again, one lecture today, one lecture probably around the end of this week, and then we are done with all the lectures. So hopefully you will get enough time to study, and this will basically be that there should be plenty of time basically for you guys to study. So today is the 17th, right? 16th. It's actually the 16th. Well, close to be the 17th since it's 11 a.m. now. But yeah, so the 17th. So expect the last lecture on the 20th, which I think is pretty generous when it comes to basically the time you can study in. So let's rewind a little bit and talk about how the whole computer system architecture looks like in the von Neumann architecture. You basically have the CPU, you have the memory, you have the memory bus that is basically connecting both the CPU and the memory. And then you have a general I/O bus where you have things such as your graphics card connected, your mouse, your keyboard, and these things might also be connected there. Doesn't have to be basically through PCI, of course, um, unless it's a laptop. Well, details aside, you have a general I/O bus, and then you have a peripheral I/O bus, which is like SCSI, SATA, USB, and these basically is where most of your like other things are connected. You basically have you can have your hard disk, you can have your, since it's USB, so you can have your keyboard. You'll typically have your your keyboard also if it's laptop connected over the peripheral I/O bus, also the mouse or the touchpad or whatever. Also, there are slight differences in architectures, but most of the architectures will actually have the peripheral I/O bus where you'll have most of the other stuff. Okay, uh, so a typical device, any of these devices, basically your memory, your graphics, or your peripheral I/O devices, storage or keyboard or mouse, typically consists of two parts: the interface and the internals. So the interface is basically how you can communicate with this device. So every device, every single device that is created by humans, basically, will have some interface so that the computer can talk to that device. And it's almost pretty standardized. You have some registers, which is like status, command, and data, and you have and these three are basically what you would use to communicate between your um, your device, your hardware device, the hardware of the device, and your CPU. And then you have the internals, which can contain a microcontroller, which is sort of a smaller sized CPU, a memory, DRAM or SRAM or whatever, and some other hardware specific chips. So actually, if you look at your hard disk, most hard disks will actually have a microcontroller, which is like a small CPU, will have some form of cache or RAM, and will have some other hardware specific chips for the storage itself. Okay, So this is an example of how you would program, of how programmed I/O would be done. Basically, how you program an I/O for an I/O device. And this technique is called polling. Where you basically you have this interface that we created, like the registers, status, command, and data, and you poll on the registers. So while status equal to busy, so if the status field has busy, wait until the device is not busy. Okay, and then write to data register, and then write command to command register. Is it read? Is it write? What is the command? And then while status is busy, wait until device is done with your request. So that's a very generic piece of code. So suppose let us talk about basically a hard disk. Okay, and let us talk about hard disk where the CPU does not have any way to interleave different processes. So the CPU will just wait for I/O. It will not try to do any sort of scheduling to basically uh, cut down the total runtime of a process by running a second thread or second process in parallel until the I/O is done. So this is a technique that's called polling. So in that case, if you're trying to write, if the CPU gives a command to write some data to disk, so it will check if the disk is busy now. So while status equal to busy is it check if the disk is busy now, and until it's sorry, until it's no longer busy, it will just wait. Okay, and once the status changes from busy to basically ready or available, and this is something that will be changed by the microcontroller that is in the internals of the hard disk. So it's not something that the CPU, your main CPU, will do. It's more like the internals of the device itself. Your hard disk will do it. Will change the status from busy to available, and then your CPU, once that status is available, will write the data to the data register, and then write the command to the command register. So the command is write. Okay, so it writes to the command register write. Now, now the device. Sorry, I have not fully recovered from my my cold. So sorry again. So you write command to command register, and that command is write. So now the hard disk can basically start doing the process. So that once there is a command in the command register, the hard disk will start doing whatever it's supposed to do, and then the CPU will wait for the hard disk to basically tell it that, well, I am done with your request. Okay, so polling is an expensive process because you have the CPU waiting for every CPU for every I/O device, as we already discussed. So what we try to do is to try to lower the CPU overhead with interrupts. So we have invented interrupts. I mean, this is sort of a recap on what we said during the first few lectures. And basically, an interrupt is basically something that tells the CPU, now I'm done with this. Instead of the CPU waiting, busy waiting, doing nothing basically, the CPU can go do something else. And when it gets the interrupt, it knows that the write process is over, or it knows that the device is ready, or whatever. So the operating system can issue an I/O request, put the calling process to sleep, and context switch to another task, and then get a hardware interrupt when the process is done, basically with whatever I/O it was supposed to do. So are interrupts always the best solution? Actually not, because in some cases you actually have many interrupts coming in. Okay, so imagine a device that performs its tasks very quickly. The first poll usually finds the device to be done with the task. So if it's a very fast device, then you will basically you don't really care if it takes if you do the polling or not, because if the device is as fast as the CPU, then by the time, but the next time the CPU asks for anything, the device is already done. So using an interrupt will actually slow down the system, and switching to another process handling the interrupts and switching back to the issuing process is expensive. So that basically means that polling can be cheaper in that case. So if a device is fast, polling might be your best solution, not actually interrupts. And and then we have to ask ourselves, what if we do not know the speed of the device, which is the case in many cases, and what if the device is sometimes fast and sometimes slow? So it might be best to use a hybrid approach that polls for a little while, and then if the device is basically slow, is not finished, it uses interrupts. This two-phased approach may actually give you the best of both worlds. You will lose a bit of so if it's a slow device and every time you wait for a while and then you leave the device, and you wait for an interrupt, then you're going to lose some time in the polling process that you do in the beginning. But still, I mean, for a device that shows variable speeds, then this is actually a good solution. And another reason why basically we do not choose interrupts always is that you might end up with a live lock, and this is what I was saying about having lots of interrupts happening at the same time. So this is very common, for example, in web servers where you basically put your website and you become famous. You get slash dotted, as we say, and people start looking up your web page. And all of a sudden, instead of basically two people caring about you in the universe, all of a sudden the whole world cares about you. And this has happened to multiple occasions. So I would give you an example that just happened. The woman in New York, the woman in California who went into the YouTube and started shooting at YouTube employees because basically YouTube was blocking some of her videos. She had a website, and that website was probably something that nobody really cared about. But once the news were out, they actually all of the news, the major news sites, linked to her website, and all of a sudden there were, I mean, for the bad of, I mean, she was a bad person. That's a bad example, but I'm just saying that all of a sudden this woman who was completely unknown, nobody really cared about her in the universe. Well, she had some followers for her views, but otherwise nobody really cared about her. I mean, I as a person would have never gone to her website if it wasn't for that case. So all of a sudden people become popular, and when people become popular, lots of people basically start trying to access their web pages. And suppose that I cure cancer tomorrow, basically, and all of a sudden everyone is interested. Who am I? And people start logging onto my university web page, and they basically have killed the web servers of the university. Another example is when Stephen Hawking died. The Cambridge website basically collapsed, so nobody could access it because everybody all of a sudden was interested in downloading his PhD thesis, which is a very weird thing. Nobody really cared about Hawking's PhD thesis during his life. I mean, yeah, probably some people cared about it, but it wasn't like the whole universe trying to read it. But the news websites, they just said that, Stephen Hawking, his PhD thesis in Cambridge was very nice. It explained to us whatever, and people were all of a sudden very interested in interstellar physics, and they downloaded a PhD that is full of equations that they will never understand, even no matter how hard they try, because I bet Hawking himself had a hard time understanding it. So this is the sort of things that you get on website servers. So what would happen typically in these cases that you get live locked. So there are too many interrupts. There are like every single time the processor tries to do something, there is a new interrupt. Okay, and that basically results in basically nothing being done. Everybody's live locked. Okay. Because, well, user level process will never run. Okay, So this is an example. If you're using polling on the other hand, then what you'll get is that some requests will be dropped. Okay, some requests will be serviced, and some requests will be queued. Uh, so this is basically uh, on, on average you would never use polling in a web server, but if you could use polling when basically these traffic servers, when you get slash dotted, uh, then that can actually save you some work and some time.